This is the worksheet review problem 1. So here's a problem from chapter 1. And we have given that the current flow in milliamps flowing through a wire is given by, and then we have this piecewise function. We're supposed to sketch the current versus time and the charge versus time. So we'll start with the current. And the current is in milliamps, and time is in seconds. And we have something for below 0, something from 0 to 5, and then something different for greater than 5. To get an idea as to what our scale is going to be, when we look at this last part, and the 30 in front, that's as big as this exponential can be. E to a negative number is going to be decaying, and so the biggest we can get is 30, so we'll do by tens, 10, 20, 30. Now for t less than 0, we have 0. So right there. And for t between 0 and 5, we have 6t. That's a straight line. You only need 2 points to graph a straight line. At 0, 6 times 0 is 0. And at 5, the other endpoint, 6 times 5 is 30. And that's our graph for t between 0 and 5. Now for t greater than 5, we have this decaying exponential. We know that it will be approaching the x-axis as an asymptote, because as t goes to infinity, this is e to the minus infinity, which is going to be 0. And so we also see that we have this t minus 5 here. So this is like a shift of the graph 30e to the minus 0.6t, 5 units to the right. So at t equals 5, that would be like 30e to the minus 0.6t at 0. But anyway, if you plug in 5, minus 0.6 times 5 minus 5, 5 minus 5 is 0. That's e to the 0 is 1. And 30 times 1 is 30. So at 5, it is 30. Now we know it's going to be approaching the x-axis, and it'll have a decaying shape. But to get an idea as to what the value might be at some other points, let's just plug them in and see what we've got. So t and I of t, let's just see, we've got 6 and we've got 7. And just do a quick calculation. At t equals 6, we have a value of 16.4 milliamps. And at t equals 7, we have a value of 9.03, 9.04 milliamps. So if we just graph those 2 points, we get an idea of the general shape here. So at 6, we're at 16, and at 7, we're at 9. So we know it'll look like this. So now we're supposed to sketch the current versus time. I'm sorry, the charge versus time. So we will have the charge in millicoulombs, and our time will still be in seconds. And 2, 3, 4, 5. And let's see what we've got here. So we know that the current before t equals 0 is 0, and so that means the charge accumulated up to 0 is 0. And so we can just fill that in. And now we want to see what the charge is between 0 and 5. And so the charge between 0 and 5 will be the integral from minus infinity, so all the charge that's built up from minus infinity, we know it doesn't actually start building any until we get to 0, to t of 6t dt. And that equals 3t squared, which is a parabola. And we can see that at 0, our parabola has value 0, and at 5, it has value 3 times 5 squared is 25. So that'll be 75. So let's draw an axis here in multiples of 25. And if you do the actual calculations first, that'll give you a better idea as to how big to make the axis, but we haven't done the calculation yet. So let's see. So our parabola is 0, 0. At 1, it's 3. At 2, 2 squared is 4 times 3 is 12. At 4, 4 squared is 16 times 3 is 48. Oh, I skipped 3? Yeah, I did. So 3 squared is 9 times 3 is 27. And at 5, 5 squared times 3 is 75. So a parabolic shape there. Now, we want this to be continuous because you can't have a discontinuous buildup of charge, and so we'll see if that works here for our next segment. So for our next segment, we're going to have that q of t equals the integral from 0 to 5 of 6t dt. So you have all the charge that you got in the first 5 seconds, and then plus the integral from 5 to t of 30e to the minus 0.6 t minus 5 dt. So the integral of 6t is 3t squared from 0 to 5, and the integral of 30e to the minus 0.6t to the minus 5 is going to be 30 e to the minus 0.6 t minus 5 divided by negative 0.6. So we plug in 5 here, we get 25 times 3 is 75. We divide 30 by negative 0.6, and we get negative 50 e to the minus 0.6 t minus 5. But what I forgot here is that this is evaluated from 5 to t, so we're not quite done yet. So we plug in t, and we get 75 minus 50 e to the minus 0.6 t minus 5. And then we subtract plugging in 5, so when we plug in 5, 5 minus 5 is 0, e to the 0 is 1, so that's 50. And now I factor out a negative 50, and just do that so it'll look like other problems that look like this. It'll end up with a 1 minus e to a negative power. So I factor out a negative 50, and a negative 50 and the minus sign here become a plus 50. This negative 50 becomes a 1, and this becomes a minus e to the minus 0.6 t minus 5. And we can see that this is going to be something that is approaching an asymptote. So when you've got this kind of format, it'll be increasing to some particular point, to an asymptote. And to find out what that would be, you see what the limit is as t goes to infinity. So as t goes to infinity, this becomes e to the negative infinity, which is 0. And so this becomes 1. So 75 plus 50 is 125. So the asymptote that it's approaching is 125. And at t equals 5, if we plug in 5 here, this is e to the 0, which is 1. 1 minus 1 is 0. 50 times 0 is 0, so it's 75. So it is continuous, so that's nice. And we know that it's going to be approaching this asymptote here. And just to get an idea as to what the curve is actually going to look like, we'll do like we did with the current, and we'll just calculate for 6 and 7. And at t equals 6, I get 98. And at t equals 7, I get 110. So t equals 6, we have 98. T equals 7, we have 110. So we're going to have a curve that looks something like this. And that would be our graph for the current. I of t in milliamps is this one, and for our charge, our accumulated charge in millicoulombs, is this one.